Hello guys, I am Saurabh Gupta. I am a student of IIT Bombay and currently I am studying mechanical engineering. I have written my JEE in the year 2010 and secured an EIR of 443. I have cleared the second stage of chemistry Olympiad conducted by HBCSE. And now we will discuss some concepts about alkenes and alkynes in this lecture. This is the advanced level of this topic, so you must be thorough with the theory which I have taught in the basic lecture, or follow the NCERT book or any other standard textbook, so that you can, because there are so many reactions in this chapter and there are so many mechanisms, so if we do some question, you don't get confused about the mechanism or the reaction, so that you can properly follow me in each and every question. So let us begin. Let us first start with some basic questions. You have to tell me what is the most stable product or major product of this reaction. When I take this alkyl halide and treat it with CH3O minus K plus and heat it. Now this is a tertiary alkyl halide and you have to tell me what is the major product in this reaction. Now clearly the major product, this is a dehydrohalogenation reaction, which is a preparation method for the alkene, and this is elimination reaction, and hence it can proceed through both E1 and E2 mechanisms. And here as we see that if this Br goes off, then we get a very stable carbocation, and hence the method which we follow here is E1, and the base is also not so bulky, so that means E1 must be a preferred mechanism for this. So if we write the mechanism, then our step 1. What is the step 1 in a E1 mechanism? It is obviously the formation of carbocation, which is the intermediate. So now we get this type of carbocation if we remove Br minus Br minus, fine. Now with this intermediate, will this thing rearrange? No. This is a tertiary carbocation, and tertiary carbocations do rearrange unless and until there is a case of ring expansion. So this carbocation won't rearrange. That means simply what we can do is we can take this CH3O minus, which is a base, and abstract one of the alpha hydrogens, one of the beta hydrogens. Now what are the beta hydrogens that are available to us? We have 3 beta hydrogens over here, we have 3 over here, and we have 2 over here. And now whenever such a choice comes, we know that to make the transition state more stable, we go for the more substituted alkenes. That means we go for the transition state which will give us a more substituted alkene, and that is also called the Sedgwick rule, and so we are going to follow this here. So, and this is not a bulky base also, because if it was a bulky base, then you have to follow the Hofmann elimination and write a less substituted alkene. But this is a small base, so we write our final product as that this base abstracts this hydrogen or this hydrogen, and hence our final product becomes hydrogen double bond carbon CH3 CH3. As you can see that this is a very much substituted alkene, and which has got 9 hyperconjugation structures. So, and this is the most stable alkene which is possible from this reaction. Fine, let us move on to the next question. A very similar question, but with a small change. What if I change the base to some other one? If I change the base to, suppose, tertiary butoxide. What is this tertiary butoxide? Tertiary butoxide is this O minus K plus. So this is our base now. Now tell me what is the major product in this reaction. Again, this is an elimination reaction, and if we go by even mechanism, then what we get is this. First we get our stable carbocation, which is the same as it was in the previous case, but now which hydrogen will the base abstract? Is it the same hydrogen as the previous one or some other different hydrogen? Clearly the answer is something different, because now the base is quite bulky and we have to go for the Hofmann elimination. So tertiary butoxide abstracts one of these 6 hydrogens. Any one it can abstract, and abstracts one of those 6, and the final alkene which we get is this C, double bond C, then we have a C here, hydrogen, hydrogen, and we have 4 carbons here. Fine. So this is the final product that we get. 1, 2, 3, 4. Sorry, you have 3 carbons only. So this is the final product that we get, and this is obviously a very less substituted alkene. But we know that Hofmann product is, Hofmann rule says that a less substituted alkene will be produced. Fine, no problem. Let's move on to the next question. So this was just to remind you the E1 and E2 mechanisms and the Sedgwick and Hofmann rules. Very simple, they are just based on the stability of the transition states. Now let me change our product, or let me change our reactant a bit. What if I change it to, now we have only heat, we don't have any other reagent, but I have changed my reactant to N plus and CH3 thrice OH minus. So now this is our reactant and C is present over here. Fine. Now if I heat this reactant, what is the major product that I get? Now quite obviously, since we are discussing it under alkenes and alkynes, the product must be either alkene or alkynes. And now since we have discussed the previous 2 questions based on alkenes, preparation of alkenes, this is also a method for preparation of alkenes. Let us see how. For preparation of alkenes, okay, forget about preparation of alkenes. If this is just a random question given to you, how would you approach this question? The approach is very, very important in organic chemistry, because without that approach, it is very, very difficult to solve any question. Now, let us approach this. We have N plus and we have CH3 thrice O minus. Now that means that if somehow I can cleave this bond, I will get a very stable carbocation, and I will get a very stable species over here also, because right now our species is, this is some R group, N, CH3, 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 and N has got a positive charge like this, which is stabilized by the negative OH minus charge. Fine. Now suppose I cleave this bond, then what happens? Then what I get is a stable carbocation, but still carbocation are very, very reactive. If it is stable also, then also we should try to move the reaction in such a way that intermediates are not produced. But here we don't have any other choice other than producing a carbocation, and we will have this amine, tertiary amine, which is going free. Nitrogen will get its 2 lone pair back, because it will just take away the electrons this way. Fine. Now what to do with this carbocation? We have got a carbocation, as I told you it is a reactive species, so what to do with it? With what we can do is, we can use this OH minus. So if we use this OH minus over here, which can act like a base, and even heat is provided, so we have ideal conditions for the formation of an alkene. And now tell me, what is the alkene that will be forming? Whether it will be according to the Sedgwick rule or the Hofmann rule. Now the thing is, here it is acting not as a E1 mechanism, but it is something like a E2 mechanism. That is, this OH minus, it is observed that it takes away the hydrogen according to the Hofmann elimination, that is from a less sterically hindered carbon, and then simultaneously this nitrogen gets its lone pair back. So what we finally get is that this OH minus abstracts the hydrogen from a less substituted carbon or a less hindered carbon and gives us a Hofmann product. This is called the Hofmann elimination. We have the Hofmann rule and the Sedgwick rule for the even mechanisms, and based on that terminology, this type of elimination is called Hofmann elimination, because here the OH minus abstracts the hydrogen from a less sterically hindered carbon. So this is a very nice reaction where here we are using ammonium salts and we are getting an alkene using Hofmann elimination. This is a very important reaction, frequently asked in JEE. So this was another method, another preparation method of alkenes. So to the list of the preparation methods, which is already huge, we add this method of Hofmann elimination also. Fine. Moving on to the next question. Now let us see some questions, some applications based on the properties or the chemical properties of alkenes. The question says that there is a compound A which consumes 5 moles of hydrogen to give this compound. We have a ring and we have a butyl group. Fine. A compound A consumes 5 moles of hydrogen to give us this kind of a compound, and further information is given about that compound, which says that on ozonolysis A gives these 4 compounds. It gives double bond O, double bond O and double bond OH. Fine. Then another compound is double bond O, double bond O. Fine. Another is this, and just to make it right, we have we have this aldehyde group itself, and this is also an aldehyde group, and fine, all are aldehyde groups. Now this one we have here double bond O, then we have a carboxylic acid, double bond OH and hydrogen, plus we have formic acid, HC double bond OH. Now what are we given here is some data regarding a compound which on hydrogenation gives this type of structure. That means the skeletal structure is this much and the double bonds and triple bonds are located somewhere in this molecule. Now on ozonolysis we have these many compounds, so that gives us the idea where these compounds, where the location of double bonds and triple bonds might be present. So let us start our analysis. First of all thing, these two, if you observe, we are getting a carboxylic acid, and if we get a carboxylic acid in ozonolysis of any compound, that must be alkynes, because that cannot be alkenes. Alkenes we will get only aldehydes and ketones alone. We do not get carboxylic acids, we get that only in alkynes. And one more thing to notice is that this is a formic acid, that means it must be a terminal alkyne. Why? Because if you take any alkyne like this, if you break it, you will not get formic acid, you will get some ethanoic acid, or at least a 2 carbon acid. So what we have analyzed is till now that there must be a terminal alkyne. So we can keep 2 double bonds over here like this. We have got a terminal alkyne. Fine. So we have identified our at least 2 of the pi bonds. It requires 5 moles of H2. That gives us an idea that there must be totally 5 pi bonds, and we have already got 2. So our requirement or our job is now to calculate the rest of the 3, whether they are alkynes or whether they are alkenes. Now as you can see that there are no more carboxylic acids, only these 2 carbons have got carboxylic acid groups. So that means there is only 1 alkyne and rest all are alkenes. That means we have to find out 3 double bonds, the location of 3 double bonds. Fine. Now with the help of this we can at least start searching. The next to the alkyne carbon we have got a carbon atom which has a double bond O. So that means the carbon atom must be having a double bond. So double bond will be over here, because C is this carbon, next carbon is this carbon, and this has got double bond with some carbon. So that must be this carbon. So fine. Now this carbon must be this carbon, and it says that this carbon has also got a double bond. That is, if you cleave it like this, then you get a ring plus this, and you get something like a structure. If you cleave here, you get one formic acid. If you cleave over here, you get C, double bond OH, single bond C, carboxylic acid, which is this structure. That means till here at least it is correct. Fine. Now the thing is, it can be this or it can be this, because we have an aldehyde group over here also. So it might be possible that this double bond actually represents the whole this thing. So this carbon might be this carbon, or this carbon might be this carbon. So we have to guarantee that which one of these two is correct. We have that to find out. Fine. Suppose that this green carbon is this one. We will take a black one also, and this green carbon is this green carbon. Suppose that is the case. Then we see that next to this green carbon we have a double bond O. That means the carbon adjacent to this carbon also has got a double bond. Suppose it is something like this. Fine, it might be like that. Now if you cleave this, what do you get? If you cleave a double bond over here, what you get is one carbon, and we get one group which is something like this, and we get OH here and O here. Because this carbon contains two alkyl groups, it will give us a ketone rather than an aldehyde. So that means this carbon is not this carbon must be this carbon. You understand why? Because the carbon next to this carbon is giving an aldehyde. That means there must be a double bond there. And if we put a double bond over here or over here, we see that we will get a ketone rather than aldehyde. So our deductions say that we have to follow this. So this structure is wrong. We will rewrite the structure, redraw the structure here. Fine. Now, if we go according to this structure, that is this carbon is this. It says again that the next carbon is having a double bond, but here we do have a ketone. That means our assumptions are correct and we are going in the correct direction. We have got a ketone. So now let us track that carbon. This carbon is the blue carbon. The next carbon is this carbon, which is this carbon. The next carbon is this carbon, which is this carbon. Finally, we have one more carbon over here, and which says that this carbon must be having a double bond, which must be a double bond like this, or it might be like this. But if you have a double bond like this, then this carbon will be cleaved and you will have a group like ketone. And so you can see that the double bond cannot come over here, because then you won't get this type of a group. You will get some other kind of a group. So let us join the bond again over here. Fine. Now to finally confirm our structure, what we do is we break the structure over here and we break the structure over here. Here what do we get? One carbon, double bond O, H. This carbon connected to one carbon. This carbon is connected to another carbon which has got a ketone group, which is connected to another carbon which has got an aldehyde group. Now compare this with this. Now again we get a wrong answer, that is this group cannot be this group, and this group is not looking like this group also. because between a ketone and aldehyde we have 2 carbons and here we have only 1 carbon. So there is only one solution for this, and that is this pi bond is correct, but this pi bond we have to make a change over here, that we make it over here. So this is a final structure that we have 1, 2, 3, 4, 5 pi bonds, and hence it consumes 5 moles of H2, and it also follows this ozonolysis products. So ozonolysis questions are very tricky. You need to identify which combines with what, which is compatible with what. So if this carbon represented this carbon, we got a contradiction. If this carbon represented this carbon, then we could proceed further and we could finally determine the whole structure. Fine. So we are done with this question. Now let us do the next question. The next question says, it is actually a multi-correct question, and it says that propene can be obtained from which of the following compounds. The first compound is ethyl alcohol. Ethyl alcohol. The second compound is methyl alcohol. Methyl alcohol. The third compound is propyl alcohol. Propyl alcohol. The fourth compound is isopropyl alcohol. Isopropyl alcohol. Fine. Now you have to tell me propene can be obtained from which of these alcohols. Let us draw first the structure of these alcohols. We have alcohol, ethyl alcohol, we have alcohol like this. Now can propene be obtained from this? First of all, think the number of alcohols, the number of carbons in this alcohol is 2, which does not match with the number of carbons in the alkene, and we do not have any method in which the number of carbon can be raised in an alcohol and we get an alkene. So that means definitely propyl alcohol, the ethyl alcohol and methyl alcohol are incorrect. Now let us see whether we can get propene from the other 2 alcohols. Definitely from propyl alcohol, at least we can get propene. Propene, just do acid catalyzed hydrogenation, dehydration, and you will get propene. Just put acid catalyzed dehydration and you will get propene. What about isopropyl alcohol? Isopropyl alcohol, which is this type of structure. Now can you get propene from this? Definitely you can get propene from this. Again do H plus and heat and we get a propene. So that means these 2 are the correct answers. Now propene, there are no isomers, so this turned out to be very easy questions, but we know that these reactions are very regiospecific and this won't give all the alkenes. So if a particular alkene is given, you have to choose a very particular alcohol, because carbocation is formed in case of acid dehydration and the reagents can take place. So we have to be very careful when we choose alcohol for producing alkene through the acid catalyzed dehydration. If you are using the other 2 methods, the hydroboration oxidation and oxymercuration demercuration, then you have got no problem, because we can control the whole reaction. We can decide the reactant according to the product. Now let us go towards another interesting question, which is a subjective question which can fetch you a lot of marks. The question says that there are 2 alkenes A and B. The properties of these 2 alkenes are that on vigorous oxidation with KMnO4, this gives a carbonyl compound which has exactly 4 carbons, and it gives an acid which also has 4 carbons. Fine. Now this thing B gives an acid E and a compound G, which is a carbonyl compound, and this compound, the specialty is that it contains a carbon, it contains 1 carbon atom on which no two groups are identical. Fine. You have to tell, and the final clue given is that the number of hyperconjugation structures of A is exactly one more than that of B. One more than that of B. So this is the final clue given to us, and there is some other information. Now from here, can we determine the structure of A, B, C, A, B, D, E and E, G? Oh, I think I have made a mistake. E is repeated twice. This is F. So A, B, D, E, F, G. You have to determine all the structures with proper reasoning. With this much limited amount of information, this becomes a very, very good question and an interesting one. First of all thing, KMnO4, and we know that both A and B are alkenes. That means with KMnO4, you will get a carbonyl compound only if it is a ketone. If it is an aldehyde, we will get the corresponding carboxylic acid. And here we get an acid, no problem. Here also we get a carbonyl compound and an acid. So that means we can start writing a carbonyl compound, one carbon, a carbonyl compound. That means it must be at least a ketone. So one CH3 group. One more clue is given that it contains 4 carbons. These both have 4 carbons. So we can have one CH3 and one C2H5 group like this. And if you see that, this is the only structure possible for D. Why? Because there are 4 carbons and it has to be a ketone. So either CH3 or C2H5 like this, or CH3 or C2H5 like that. Both give you identical structures, and hence this is the only possible structure for D. So let us draw it in green. The only possible structure for D is CH3, C double bond O, C2H5. This is D. Now what about E? E, if we see that there are again 4 carbons and E is an acid. So at least we will have that group, and we have 3 carbons here in some arrangement. So either we can have the 3 carbons like this, or we can have the 3 carbons in this fashion. We can have the 3 carbons like this. That is a substituted substituent. Fine. Out of these 2 structures, right now we cannot determine which is correct because no other clue is given for E. But one clue is given in the top that A, the number of hyperconjugated structures, is exactly more than that of B. So we have to make use of that clue to determine which of these 2 structures is correct. But let us first determine the whole structure of both A and B. So A has got 2 possible structures. Now we have got both the structures of D and E. That means we can get the structure of A, or the possible structures of A. Because we know if KMnO4 is there, and if you are getting a carbonyl compound or carboxylic acid, then that must be coming from the double bond. That means these 2 carbons must be the carbons in the double bond. So with that we can write the structure of the alkene, that is not a problem. But now we have to go towards F and G. F, it is simply given it is an acid, and we know that A and B are isomers. That is also given. I forgot to mention that A and B are isomers of each other. And if A and B are isomers of each other, then that means the number of carbons must be the same. That is, both must contain 8 number of carbons. That means B must also contain 8 number of carbons. Now, if we know the number of carbons in B, can we determine something? There can be any number of carbons in the acid, and there can be any number of carbons in the carbonyl compound. How can we determine what is the exact structure? For that, this clue is given, that it contains a carbon atom which has 2 non-identical groups. None of the 2 groups are identical. What does it mean? it means that it contains a chiral center. And if we draw the structure of carbonyl compound that way, so let us take first C double bond O group. Let us take a CH3 here. Let us take a CH3 here. But definitely this is not chiral. No way this is chiral. So let us take a CH3 here. Again we see that none of these groups become chiral. But if we add suppose C2H5 like this, then what happens to this carbon? Then this carbon becomes chiral. So that means we require at least 1, 2, 3, 4, 5, 6 hydrogens, 6 carbons to make this compound G chiral. We can also put a propyl group over here like this, but then if we put a propyl group over there, there is a slight problem. What is this? This is an acid, and this cannot contain just one carbon. It does not say that it is an alkyne, and if it is not an alkyne, then definitely you cannot get this kind of structure. You can get only CO2 if there is only a single carbon. That is, if it is a terminal alkene, then you will get CO2, because this is not ozonolysis, this is KMnO4 oxidation. And hence, if you want to get an acid, you must have at least 2 carbons in that, because that is at least on the second carbon the alkene must be present, because otherwise if it is a terminal alkene, then you will get carbon dioxide and not formic acid. So that is the trick here, that this acid should contain at least 2 atoms. So this acid must be something like this. And we have also got one condition, that for this compound to be chiral, it needs at least 6 carbons. So that total adds up to 8, and hence we have the structure for both F and G. So you see how nice this question is. With just words, just giving small clues, we can determine the whole structure, that is F, G and D. But the structure of E is yet still undetermined. How do you determine that? For that we need to draw first both the alkenes. So if you draw the alkene over here, I think we can draw the alkene very easily, because there is only acetic acid is there. So the alkene will be something like this. This is the structure of alkene B. Fine, no problem. Count the number of hyperconjugating structures. We have here 1, 3 plus 3, 6. No. This is, 6, because here we have CH3, here we have got a hydrogen. So this is a double bond, and the number of hyperconjugating structures include these 3 hydrogens, and we have got 1 hydrogen over here, which again I can write it in blue. So that means these are the 7, 3 plus 3, 6 plus 1, 7 hydrogens, which are giving you the 7 hyperconjugating structures. Now what? Now next we need to determine which of these 2 structures of E gives us 8 hyperconjugating structures. Why? Because the question says that the number of hyperconjugating structures of A is exactly 1 more than that of B. So that means if we do that, we will get, let me draw the structure of A now. Structure of A will be a bit complicated, because we have CH3, C, C2H5. So if we draw the number of hydrogens also, CH2, CH3, then we have a double bond, C. Now first let me take this structure. Now if we see, now this contains double bond, and this is the double bond carbon, which has 1 methyl group. So this will contribute to the hyperconjugate structures, and it has got 1 ethyl group, which is same as this, and it has got 1 ethyl group, CH2, CH3. Now tell me which structure is correct, whether this is the structure or this one is the structure. Here we have 3 plus 3, 6 plus 2, 8 plus 2, 10 hyperconjugating structures. But if we do this thing, you will observe that there are exactly 8 hyperconjugating structures, because then this CH3 won't be there. We have only this CH3, that is 3, 2 plus 2, 5, and we will have 3 hyperconjugating structures from here. So now what we find is that this is having exactly one hyperconjugating structure. Actually, there is a small change in the question. This is not more. Actually, this is one less. My mistake. This is exactly one less. But that doesn't matter. The logic over here is you have to see what is the final relationship between the hyperconjugating structures. If we have this hydrogen, then there will be only 2 hydrogens over here. So we will get exactly 6 hyperconjugated structures. Here we got 8 hyperconjugated structures. So 5 plus 2, 7 and 8, because of these two hydrogens. So now that means that each clue has given us one structure. This clue, 4 carbons, gave us one structure. 4 carbons didn't give us any structure, it gave us 2 possibilities. This clue gave us this structure, the isomerism gave us this structure, and finally this clue gave us which one of these is the correct structure. So this was a very nice question, and now let us move on. Now let us do another very nice question, which is based on something. We have to find out what is the question based on. Now there are a variety of questions which are asked in JEE, and we are also going to do a variety of questions. Match the following, comprehension, associative reasoning, multi-correct we have already seen, subjective questions we are doing, and we will be doing another subjective questions. So the next subjective question is an organic compound A of molecular formula C5H8. Now this compound when treated with sodium in liquid ammonia, what does it give? Followed with reaction with N-propyl bromide yields B. Followed with reaction with N-propyl bromide gives B. So there are 2 steps, and after the 2 steps we get a structure of B. Next, what we get is the molecular formula of B is C8H14. Fine. Next, A gives ketone C. This is again A. This is giving a ketone C. It is given that it is a ketone, and C5H10O. Very lucky, you have been even given the molecular formula for the ketone. Fine. When treated with dilute H2SO4, and HgSO4. Fine. Now B on oxidation with alkaline KMnO4. This is B. B on oxidation with alkaline KMnO4 gives us 2 isomeric acids D and E. So the relation is they are isomeric acids. Fine. Then the molecular formula of the acids is also given, C4H8O2. Right. Now give the A structures from A to V with proper reasoning again. So this is also again a very nice question, but not as good as the previous question, because here we have been given some molecular formula and something. But the previous question, just words. There was not even mention of even a single molecular formula of any of the structures. So now let's see the structure. We have got A, which reacts with Na liquid ammonia and N-propyl bromide to give us C8H14. Now what clue does the first reaction give you? It is a characteristic reaction of alkyne and not alkenes. So if it is a characteristic reaction of alkynes, and moreover, to be specific, it is a characteristic reaction of a terminal alkyne. So that means some clue about the structure of A, that it is at least a terminal alkyne. Now, from the molecular formula, you can also calculate one more thing, that is the number of unsaturations. The number of unsaturations, suppose it were a perfect hydrocarbon, a perfect saturated hydrocarbon. What would be the molecular formula? C5H12, pentane. Now, the molecular formula has been reduced to C5H8. That means how many unsaturations? You see that there are 4 hydrogens gone, and if you divide 4 by 2, you get 2 unsaturations. And in fact, we have already got 2 unsaturations, that is one pi bond and another pi bond. So that means there are no more unsaturations, and it is simple, linear, or it may not be linear, it might be branched also, but we will get while we solve that question, rest of the question. So that means there are no more unsaturations, that means A has only the properties of a terminal alkyne, and hence it will undergo the reactions of the terminal alkyne. Now, this structure, we have 3 carbons left, so either this is the structure, or a possible structure is C triple bond C. We can have a structure like this, that is with a substituent over there. Now, which of the 2 structures is correct? Right now we don't know. Fine. Now, when it reacts with N-propyl bromide, we get C8H14. So B structure also will be in doubt, because terminal alkyne, you know, in Na liquid ammonia you will get alkanide ion, Na liquid ammonia you will get this ion, and N-propyl bromide will give you what? Will give you nothing but, if Br is this, N-propyl bromide, this is not any structure, normal linear structure. This reaction, this carbon attacks this, so bromine goes away. So you will have nothing but at the end carbon, you will have 3 extra carbons, nothing more, nothing less. So now from that structure we have to, but that does not give any clue about the previous 3 carbons. We have just added extra 3 carbons over here in a linear fashion. But what about the previous 3 carbons? We are still in doubt about that structure. Now for that we have this alkaline K-4. That is, if we cleave this alkyne using alkaline K-4, that means it will give us carboxylic acids, and since we are getting isomeric acids, that means we can have some clue about the structures. Let us see whether we will get any clue about the structures. So right now our B is this kind of, suppose we go with this structure, fine. Now if I cleave this, what I get is CCC, this black carbon, and we have double bond OH. No problem. If we cleave this, then we have CCC, which actually I should write with blue, CCC, and then we have got this black carbon and double bond OH. Now B on reaction with alkaline K-4 gives us 2 isomeric acids. What we observe over here is we are getting the same acid and not the isomeric acids. Identical structures are not isomers because they do not differ in any of the properties. Now, so that means this structure is cancelled off. So this structure is definitely wrong. So finally we are left with only one structure for A, and that is this, and you can as clearly see that this will give you a substituted butanoic acid, but this will give you a straight butanoic acid. That means they will be isomers of each other, and to be precise, they will be structural isomers of each other, and hence the correct structure for A must be that. This is the correct structure for A. So we have identified correct structure for A. Correct structure for B would be C triple bond C, 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 C. This is the correct structure for B. What about correct structure for D and E? You can happily write it. This must be D, and you can write something like this as E. It doesn't matter which one you give D, which one you give E, because no more properties are mentioned. Fine. We are only left to identify the structure of C. Let us do that. Now we have an alkyne, A alkyne, treated with dilute H2SO4 and HgSO4, giving us a ketone. How does it do that? We have seen this reaction earlier. If suppose this is the case, then we will get first H2SO4, we will get an alcohol, and that would be an enol. As we know it, we get an alcohol like this, double bond C. This further is actually undergoing tautomerism and giving us the ketone, the required ketone, which is in this manner. So this is the required ketone with isopropyl group and a methyl group as the R and the R dash group respectively. So that was the ketone, this was the structure C, so we can happily write it this as C. So hence we have solved the question very easily by just applying little bit of logic, some molecular structure, molecular formula, some known reactions, some common sense also. Fine, so this question is done. Now let us move on to the next question. The next question is an assertion reasoning type. So assertion reasoning type questions, you have to be very careful with the options because they always change the options. That is, A, B, C, D correspond to different meanings. In some question papers, A correspond to correct reason as well as correct explanation. In B corresponds to something else, C corresponds to something else. But here we will follow the normal convention. A is when the reason is true and is correct explanation, and so on. But please read the question paper before you follow instructions before you answer such a question. Now the statement for our assertion reason is statement 1, alkyl fluoride. Yes, very nice. Alkyl fluoride always gives Hoffman product in dehydrohalogenation. Hoffman product in dehydrohalogenation. Fine. Now what is the statement 2? Statement 2 suggests that statement 2, fluoro group is very good nucleophile, good nucleophilic leaving group. Now we have the two statements over here, and you have to tell me whether what is the relationship between them or whether the two statements are correct or not. First, let us see the validity of the first statement. Alkyl fluoride always gives Hoffman product in dehydrohalogenation. Let us consider a substance which contains the alkyl fluoride. So suppose we have alkyl fluoride like this. We have CH3 over here, and we have CH3 over here, and CH2 over here, and one hydrogen over here. Now, how do you do the dehydrohalogenation for this compound? First of all thing, in alkyl fluorides it is observed that the dehydrohalogenation follows a different mechanism. It is even but with a difference of even Cb. This mechanism is called unimolecular elimination conjugate base. That is, it happens with the conjugate base of this alkyl fluoride. So that means this gives us a clue about the first step of the reaction, that might be like the base abstracts an hydrogen and convert this into a carbon ion. That alone gives us the conjugate base and nothing else. So the base right now should abstract a hydrogen from one of the carbons over here, such that you get a stable carbon ion. And moreover, this base has to be a very strong base because you are abstracting hydrogen from a carbon before the fluorine has left the molecule. If the fluorine is still there in the molecule, then it is very difficult to abstract the hydrogen, because there is no reason why the hydrogen should be acidic. But still, if we use a strong base, that hydrogen can be abstracted. If we use a strong base, will this hydrogen or will this hydrogen be abstracted? Now the thing is, we will get a carbon ion. If we abstract a hydrogen, we get a carbon ion, and the carbon ion stability must be, or the formation of the carbon ion must be, the slowest step. So in the slowest step, we have to see the stability of the carbon ion, so that the transition state is more stable and we get a fast reaction. So if we see which carbon ion will be more stable, we can clearly observe that this must be the most stable carbon ion, because here we have some hyperconjugation in inductive effect. Now if we get the carbon ion from here, that is the base abstracts the hydrogen from this carbon, then we have carbon ion, carbon, hydrogen, fluorine, CH2, CH3. Fine. Now what is the next step over here? Immediately, this is very stable carbon ion. Why? Because there is a fluorine group there. It is a very highly electron withdrawing group, and hence it makes the carbon ion stable. Now what is the next step? We can very easily guess that this carbon ion donates its electron density here and fluorine leaves. So we get C double bond C, hydrogen, and CH2, CH3 plus F minus. So now you observe that you get a Hofmann product instead of a Sergev product, and you will always get a Hofmann product because of the formation of the carbon ion. So that means our statement 1 is actually true. What about statement 2? Fluoro group is very good nucleophilic leaving group. Now both the statements are wrong. Why? Because neither fluorine is a good nucleophile, neither it is a good leaving group. Definitely it is not any way, no chance that it is a very good leaving group, because fluorine is a very strong base. So hence it cannot be a good leaving group. So we got our answer. Statement 2 is actually false, so I should write it with red. Statement 2 is false, hence our correct answer would be, if we follow normal conventions, it is C. Fine. So this was actually a reasoning question, which is also done. Let us move on to the next question. Now the next question is, you have to tell some order. What is the order which is observed and which is right? Now you have to tell me what is the order of HCl addition on the following alkenes: CH2, C double bond O, okay, there is one more carbon in middle, C double bond O, OH, first alkene, there is a double bond over here, second alkene, CH2, CH2, third alkene, we have C, C double bond CH2, and fourth alkene we have C, CH3 twice, C, CH3 twice, C double bond C. Now you have to tell me what is the order of the rates of reaction of the reaction with HCl. As we know that there is alkene present everywhere in the compound, so that means it must be addition of HCl reaction, and you have to tell me what is the order of the rates of the reaction. Now clearly the order of the rates depend on what? The carbocation stability. It follows the even mechanism, and the first step is the slowest step, and the rate of the reaction definitely depends only on the slowest step. So let us see in which case the carbon ion or the carbocation is very much stable. If we form a carbocation over here, we have CH3, CH3, C, C, and definitely carbocation will form here. Now here what can happen is, this CH3 can rearrange and carbocation will come over here, but that again does not give it any advantage, because here also it is secondary carbocation, and if this CH3 goes here, this also becomes the secondary carbocation, and hence no rearrangement will occur. Next question is here, out of these carbocation will definitely form over here. Here there is only one possibility. What about here? Here the carbocation would be forming something like this. Now the carbocation can also form over here, because then the carbocation will be in resonance with the double bond, and hence the order of relative rates would be the carbocation now forms over here. This is very highly reactive. This reaction is very fast because of the stability of the carbocation. This reaction will be the slowest. So if you want to give the numbering, 1 is the fastest, 4th is next, 3rd is next, and finally comes the second one. You can very easily verify this order. There is nothing to verify actually. This is obviously most stable. Then comes the secondary carbocation, primary carbocation, and here the secondary carbocation has got more number of here actually I have made a mistake, that if you see the number of hyperconjugating structures, this is also secondary carbocation, this is also secondary carbocation, and hence the second structure will be, the third structure will be the next in line. So 3rd, 4th, and then comes the first, because this is a primary carbocation, this is a secondary carbocation, and hence this is more stable than this. So this is the order. Very simple question, just based on the stability of carbocations. You have to relate the two logics, the relative rates of the addition of HCl on these compounds and the stability of carbocations. So if you know the mechanism how it undergoes addition, you can easily write what is the order of relative rates by checking the stability of the carbocation. The next question is, if you consider this reaction CaO plus C, you put some heat here, give some compound A, on reaction with water give some compound B, on reaction with HgSO4 and H2SO4, this gives us some other compound C. Now what happens? What is the structure of C and what is the compound C? Now this, you see that here we have some inorganic reactants giving us some products. Products need not be inorganic, they can be even organic. Let us see how. If you remember the preparation of alkenes or alkynes, then you will know that this CaC2 plus H2O gives you CaC2 plus H2O gives you an alkyne, C triple bond C, and this is acetylene, and now this acetylene can be the compound B if the compound A is CaC2, and yes, the compound is CaC2 because CaO plus this carbon can give you calcium carbide, that gives you A, and when it is put in water it gives you acetylene. And what happens when this acetylene is reacted with HgSO4 and H2SO4? Now tell me, this is a very famous reaction, we all know what happens. We will get an enol which is something like this, and which is finally tautomerized to what? An ethanol. This is an aldehyde. So this is very nice reaction where the inorganic components are getting converted to the organic counterparts through this process. So a nice process to convert inorganic substances to organic substances. Now let us move on to our next question, which is a subjective one, and that question is very important and it is very tricky also. That will give you the all knowledge and in-depth requirement which you require for the study of oxymercuration, demercuration and hydroboration. It will give you exactly how the mechanism is and how can you differentiate between the two. So the next question says that there are three alkenes A, B and C, A, B and C, all molecular formula C5H10, and they all are hydrogenated to yield 2-methyl butane. 2-methyl butane. Now 2-methyl butane, what is the structure? Butane and methyl present at the second position. Now this C5H10 has got how many unsaturations? The difference in, suppose we take the saturated compound which is C5H12, then the difference of hydrogen is 2, so that means the number of unsaturations would be 1. Fine. Now what? Once we have got that, that means there is only one pi bond present somewhere in the molecule, and let us see how many isomers are possible with that. Suppose I take a pi bond which is here, another molecule where the pi bond is in between, and another molecule where the pi bond is in this end. Now you see that if you take the pi bonds in this manner, and if you take a pi bond here, it is same as this isomer, so need not consider it. And these three are the only structures possible for 2-methyl butane if there is only one pi bond present. So that means these here are the three isomers, and if A, B, C are three different isomers, they have to be one of them. So now we have to use the clues to identify which one of them is A, B and C. So in this way we proceed, we select some clues, we find out whatever we can find out through those clues, and then we look for the new clues. Now the clues given to us are A and B give the same 3-degree ROH on what? Oxymercuration, demercuration. Now B and C give the same 1-degree ROH on what? On hydroboration oxidation. So now you see that there are two different processes and they are giving you 3-degree alcohols and 2-degree alcohols. Fine. Now let us do all the three processes, both the processes in this, and let us see which one gives you a 3-degree alcohol and which one gives you a 1-degree alcohol. First, doing oxymercuration, demercuration in this. It is a Markovnikov addition and without any rearrangement. That is the best part of this oxymercuration, demercuration, that you don't have any rearrangement over here. So the OH will come on this carbon and H on this carbon. But what you observe is you don't get a 3-degree ROH, you get a secondary ROH. So that means this is definitely not the structure for A, not the structure for B, and hence it is a structure for C. So the remaining two structures are left, they must be A and B respectively. But which one is A, which one is B? We have to calculate through this clue, the 1-degree ROH on the hydroxylation, on the hydroboration and oxidation. Let us see which one gives us a 1-degree ROH, and B and C should give you different 1-degree ROH. So let us do hydroxylation. First let us do hydroboration oxidation over here, because then we will compare the products with other thing. Now if we do hydroboration oxidation, we know it is anti-Markovnikov addition, and again there are no rearrangements. That is very important thing. Now what about hydroboration oxidation over here? Now here if you do hydroboration oxidation, you will get an alcohol group over here. Fine, you get an alcohol group over there. Now observe that alcohol group. It is a 2-degree alcohol group, and hence this cannot be the structure of B or C, because it says that it gives you a 1-degree alcohol on hydroboration oxidation. So now we have got that this is not B, this is not C. So what is this? This must be A. Why? Because we have got only 3 isomeric alkenes and there are only 3 isomers which are given to us. So definitely this must be A. Now just for checking that whether this is B or not, just do the hydroboration oxidation over here. Again anti-Markovnikov addition, you get a alcohol over here, and definitely these two alcohols are different. So different 1-degree alcohols on hydroboration oxidation, you get this type of structures. Fine, so we have identified what is A, B and C. Just for your convenience, I will write the answers. That is A, that is B, that is C. So this was a very nice question which told us how hydroboration oxidation can also help us in determining the structures. Fine. Now let us move on to the final question, that is a comprehension. So the comprehension has got 5 questions, so it is quite a lengthy comprehension. Let us see what is the first question of the comprehension say. The first question says that there is some alkene like this and you have got some reagents. The reagents are RCO3H and then final workup of H3O+. Now, what is this reagent? First of all, we have not seen this reagent at all in our lecture, but we have seen this at least, and that we know is the alkene. So that means the reaction must be related to the chemical properties of alkenes, and that means this must be again the electrophilic addition. This doesn't look like oxidation, although when you see the structure you will feel that it is somewhere related to oxidation. So we have C double bond O, O, OH, and we have H. So now here what we have is a peroxy linkage. We have a peroxy linkage. Now, next is what? We have a peroxy linkage and we have a alkene. So where is the electrophile? There is no electrophile right now. Now, this is the challenge to us. We have to generate the electrophile from somewhere. So how do you generate the electrophile? This is completely a new reactant, a new reaction. We don't know the mechanism. So what should we do? We apply our common sense and our logic. What we do is, we break this bond. Why? Because we know that this is a peroxy linkage and the bond is quite weak. So this bond can be broken easily. So what we do is, we break this bond and we take the advantage of that and take electrons from the p orbitals of this and donate it to this oxygen. Now you can ask, why not donate it to this oxygen and let this oxygen cleave? Because this OH minus can survive better than the HCOO minus. So that is why this is a better leaving group than that, and hence we cleave it this way. So now we have got our electrophile. That means we have got the carbocation, and here it is connected to O, C double bond O, and H plus OH minus. Now what is next? Next is we need to stabilize the carbocation, because this carbocation is a very reactive intermediate and we need to stabilize it. So stabilizing it, we can stabilize it using the lone pair of this oxygen itself. Why should it attack from outside when there is a intramolecular reaction possible? Let us do that. We have something like, now here we have getting some kind of weird molecule which we have never seen before, like this, an oxygen getting a positive charge and hydrogen. Fine. So now we have got till here. Now we don't know whether we are proceeding in the correct direction or not. So for that, I'll just give you a clue. I'll write down the options for this question. So the options are 2,3 epoxy butane, 2,3 butane diol, 2,3 butane diol. Third one, we have 2-butanone. Fourth one, we have epoxy ethane. Epoxy ethane. Fine. Now what is this epoxy? We have never seen this epoxy before. So let me show you what is epoxy. Epoxy is actually this kind of a ring. This kind of a carbon, oxygen carbon triangular link is called epoxy ring. What is 2,3 epoxy butane? If we have a link like this is present at the second and the third carbon. So between the second and the third carbon we have got an epoxy link. So there is 2,3 epoxybutane. 2,3 butane diol, we all know what it is. Diol like this. What about 2-butanone? We definitely know that. And epoxyethane is simply this compound. Hydrogen, 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 hydrogen. So that is epoxyethane. Now, what is next? Next is, do you see the structures and a similarity over here? So that means we are, with some probability, we are definitely proceeding towards the correct direction. So this is just a kind of hint that we are proceeding in the correct direction. So now what should happen? We have got an epoxy link. So now what? What we do here is, we just break this bond and get the carbocation here. So now we have got some structure like this, and we have got something like this. Now how do you stabilize a positive carbocation? We just use the OH minus generated over here to come over here, and this is finally converted to CO2. So finally our structure is this, and yes, it definitely matches with one of the options. So we have unknown reaction, unknown mechanism, we have generated our own mechanism, and we have got the correct answer also. It is very nice. So let us move on to the second question of the comprehension. So the second question of the comprehension is, again I think there is some alkene and there is some reagent, and you have to find out what is the product. Now again, in these type of questions, whenever a new reagent is given to you, we know that alkene is very familiar and we are familiar with the properties of alkenes. So that means we can definitely write the reactions. What are the possible electrophilic addition reactions, whatever it is, and we can think of a logic of how the reaction will start and propagate. Now we will consider C double bond C, CH3, CH3, this thing, and finally we have HOCl. Now we have this HOCl. What is this HOCl? I don't know what is this compound. So that means again we have to think in some manner, and we have to see the bonding, and we need to identify what is the possible reactions. Now we have an alkene, we have a compound. Where is the electrophile over here? How can we generate electrophile from this? So what we can do is, we can just do this HOCl. Now we have an electron cloud over here. The electron cloud goes and attacks this chlorine. Now why I am saying attack that chlorine and cleaves this bond like this? Oxygen is more electronegative than chlorine. So definitely OH minus should be formed and Cl plus should be formed. If the case was you had NOCl, then in that case it is possible that you get NO plus and Cl minus. So you see in HOCl and NOCl, the electrophiles are different. Electrophiles is NO plus over here, and the electrophile is Cl plus over here. So that means we have got a nice electrophile. That means we can start our reaction. So we get our carbocation, we get the electrophile, done. Now what? Now again this carbocation is planar. Stereochemistry is not known because OH can, now obviously the next molecule is OH only. OH can come from bottom, OH can come from top, and that's all. We can complete our reaction. This is simple halohydrate formation, which also occurs when we have Cl2 in H2O. So this was a nice question. Again, unknown reagent, unknown reaction, but yet a easy one. The previous one was a quite difficult one because to get all the logics is very difficult at the same time. Now we move on to the next question. Trans 2-butene on reaction with Br2CCl4. Now this is a very familiar reaction to all of us. What happens over here? Trans 2-butene like this on reaction with Br2CCl4. Br2CCl4, and we have a trans 2-butene. What type of reaction is possible? Definitely again an electrophilic addition reaction, and we also know what is the stereochemistry. Now the question what is asked is, what is the product of this reaction? I will give you 4 options. So to make your life easy, the 4 options are plus minus 3 2,3 dibromobutane. Then we have got plus 2,3 dibromobutane. Then we have minus 2,3 dibromobutane. Finally, we have mesodibromobutane. Now, out of these 4 options, which do you think is correct? Now, everything is based on optical activity, and hence we cannot say anything just from this. We need to convert everything into Fisher projections to get our final answer. For Fisher projections, you definitely require Saur's projections. And to draw the Saur's projections correctly, remember that these two are trans, so they will be opposite to each other, and even Br2 is anti, so Br2 also will be opposite to each other. So if Br2 is anti, we can draw the structure in a better way, something like this. Now Br, now we have, okay, in other words, we can keep this down, we can draw the reverse way, that will be easier for us, so that we can easily write the Fisher projections. We have Br anti to each other. Now if we choose CH3 over here, we have to put CH3 over here, and here it is hydrogen, no doubt about it. Now we need to write the Fisher projections from this one. How do you write Fisher projections from this one? Very simple. What you do is, you just take this bonds in the same plane and bonds in the opposite plane. So now if we consider a carbon, we can write Br here, and similarly we can write, this is anti, so to make the Fisher projection simple, what you do is, you rotate it in such a way that the bonds become eclipse. So before drawing the Fisher projections, remove this Br, we will draw first the eclipse one. So now rotate it such that Br aligns with Br, CH3 aligns with CH3, and H aligns with H. Rotating it, Br, CH3 and H. So now what do you observe? To be precise, the CH3 should be like this, and the Br should be something like this. CH and H and Br. Now this is perfectly vertical, and this is in this kind of shape which is parallel to that H. Now what do we have here is this kind of projection. It's very simple to write over here, CH3, CH3. Finally, from all this thing, by writing the Saur's projection correctly, by writing the Fisher projection correctly, what do we observe? That we have got a plane of symmetry. That means it is a meso compound. Why it is a meso compound? Because of 2 chiral centers. Plane of symmetry doesn't mean it is a meso compound only if there are 2 or more chiral centers, and then it contains a plane of symmetry, then it is a meso compound. Finally, 2 more questions are left. We will do one by one. The first question is, you are again given an alkene and you are given some reagent, but this time the reagent is known to you. Let us see if you can recall it. It is C double bond C, CH3, CH3, H, H, and we have CHBr3. Do you remember something? Then we have the reagent CH3 thrice, CO, and K. Now what is the major product obtained in this reaction? First of all thing, we have the alkene. Where is the electrophile? We have to generate the electrophile, and that is generated through the alpha elimination of CHBr3. This is tertiary butoxide, which gives me CBr2. So this gives me dibromocarbene. So we have generated the electrophile. This lone pair of electron is not a part of nucleophilicity, but it has got only 6 electrons, that's why it is electrophilic. So now next what? We have alkene, we have electrophile. Let us do the reaction. C double bond C, CH3 hydrogen, CH3 hydrogen, CBr2. This bond forms, and we get a stereochemistry of something like CBr. One is up the plane, one is down the plane. But what happens to the stereochemistry of these two CH3s? As I told you, the stereochemistry is retained. So you can also draw the structure in this way. Although you have been given options, but I don't think options are necessary for this question. We know what is the concept, and we know what is this structure will do. Fine, we have got the answer. Remember the stereochemistry of the two CH3s. They will remain cis if they were cis earlier in the alkene. So let us now move on to the final question of this lecture. This has been a very nice lecture. Very different types of questions with different logics, and we have seen different variety of reactions. The final question is, we have C double bond C, we have CH3, I think this is the favorite compound of the day, and we have this, we have osmium tetroxide followed by sodium bisulfite and OH minus. Now what does this give you? What is the product? To help you, I will give you the options. Meso 2,3 butane diol. Second is 2-butanol. Then we have plus 2,3 butane diol, plus minus 2,3 butane diol, and finally we have 2-butanone. Now, which is the correct answer out of the 4 options? Definitely this is fully again based on stereochemistry. Again we have no other go other than, and remember what is the stereochemistry of this osmium. The stereochemistry of this osmium tetroxide is that we get syn dihydroxylated compounds. That means we will get, if we draw the source projection directly, you remember this is the dihydroxylation reaction and the stereochemistry is syn. So again, syn means we have got a perfect match for each and everything. Suppose we have OH here, we will have OH over here. Suppose we have H over here, we will have H over here. Since it is a cis alkene, we have got two CH3s completely matching to each other. And no need to draw the Fisher projection. I can show you what is the mirror plane here itself. If you take this as the plane, that is the board perpendicular to the board, you see all the bonds are eclipsed and all the groups are matching. So hence we have got here definitely a meso compounds with a plane of symmetry, and any compound with a plane of symmetry is not a meso compound. If you see, this is a chiral center and this is also a chiral center. So just don't say that if a compound has got a plane of symmetry it is meso compound. It should have at least 2 chiral carbons for it to be called as a meso compound. So now moving on to the final question of the lecture, which is something like this. You are given a graph between the enthalpy of hydrogenation, and here are the alkenes. And the given things are P is an alkene, Q is an alkene, all are isomeric alkenes, and R is another alkene. All of them are subjected to the hydrogenation reactions. So, and obviously since they are isomeric and since there is only one double bond, that is why they give us the same alkane here. Fine. So now, what do you say about the stabilities of this PQR? That is the first question. From the above graph, identify P. Identify P if PQR are the isomers of butene. If this PQR are isomers of butene, are isomers of butene. Now, what are the isomers of butene? Possible isomers? Butene, simple one butene. We can have two butene, and I think so in positional isomers we can have only these two. But think about geometrical isomers. In geometrical isomers we can have one can be cis, another can be trans, and I think so that's all. There is only these possibilities, and we can also have this CCC and a 3 carbon and another one here, and what this one. But if you see, these three alkenes are giving us this alkane, and these three will obviously give us the alkenes which are unbranched, alkanes which are unbranched. But unfortunately this alkene, which also happens to be the isomer of butene, but this will give us a branched alkene, and we know that the potential energy or the enthalpy, you can say, of the branched alkanes and simple normal unbranched alkanes are different. So there is the catch. That exactly helps us in determining the stabilities of PQR and determining the exact structures of PQR. We know these are the only possibilities. Here we cannot have geometrical isomerism because these two hydrogens are there. Fine. Now, so that is cancelled. We can just rub it off. Understand why is it cancelled? That is very, very important in this question. Once you understand that, it is very, very simple. Fine. So, identify P. How do you identify P? What is the clue given to us? The only thing given us is they are the isomers of butene. What else? This graph. Look at this graph and tell me what is the relation you can find out. Which is more stable out of these three alkenes? How do you decide which is more stable? Which is having more potential energy. So with respect to this alkane, we have three different levels of potential energy in which P is the maximum. So P must be the most unstable of all the alkenes, which is quite obviously 1, because these two have got so many number of hyperconjugation structures more than this one butene. A very, very simple concept of the stability of alkenes which we have discussed, which says that the more number of hyperconjugation structures, the more stable is the alkene. So we have easily determined the structure of P, which is the first one. So we have solved the first question. There are two concepts in this. First one is how to eliminate the fourth structure, and the next concept is how do you actually decide the three out of the three structures which is the most unstable or the stable one, or what in deducing the meaning of what is the meaning of the graph. So moving on to the second question based on the same graph. If PQR are isomeric pentenes, if they are isomeric pentenes, then you have to determine R. So quite obviously you have to determine most stable one. Here R has to be the most stable one because the potential energy is minimum. We have a common reference level which is this alkane, unknown alkane, and we don't bother. We just want a reference level. So now, isomeric pentenes. Let us draw. 1, 2, 3, 4, 5, and we can have a pentene here. We can have a pentene here, and we can have isomers, obviously, cis and trans, and this will be the same thing. If we put over here, no, it won't be the same thing. So we will have some things like this, and here also we will have isomers, cis and trans. Cool. So now, are these the only possible structures? Yes. Why again? The same concept. If you draw with the 5-chain alkene, we can draw only these possible alkenes. Only these many structures are there. But if you take, suppose, this case or other cases than these, then you will have what? Something like you will have a branched alkane, because once you go for the fourth one, one carbon will be coming in the branch, and when you hydrogenate it, you will obviously get some different alkane or a branched alkane, which will be different in different cases, will be different in the energies. But these cases, you will have only these 3 alkenes, and of course you will have the cis and trans and cis and trans. Now, how do you determine which is R? R is given the most stable of 3 alkenes, but we have what? We have something like 5 alkenes. If you see, 2 alkenes over here and 2 alkenes over here, but there, and so here what is given is the 3 alkenes. So what we do is, we determine the most stable of the 5 alkenes itself, and that we give it as R. There are options given in the question, but I just don't want to look at the options. In the options you will find the most stable one only as given as the option. The other ones won't be given. So we just look at as a general question, and let us try to solve it. So let me tell me which of the 5 will be the most stable. This one. Oh, what I have done. This will also give me 3 alkenes only. So there is a catch. I just forgot that these 2 were the similar alkenes. So that means again we are getting the 3 alkenes. Now the question is very simple. Whether this is more stable or this is more stable. Clearly this will be more stable. Now, cis is more stable or trans is more stable. There also it was like these 2 have the same number of hyperconjugation structures, but they are the most unstable one. So we need not bother which is more stable, cis or trans. But here we have to bother, because they have asked the most stable one. So let us draw the 2 structures in detail. Now the trans will be just the opposite case. Tell me whether cis will be more stable or trans will be more stable. Quite obviously, cis is more unstable than trans. That is because of the presence of these 2 bulky groups on the same side. That gives you a lot of steric repulsion, and that decreases the stability of the alkene. And that is why we have the trans alkene, which is the answer for this question, which is the R1. The R is a trans alkene for this pentene. So that is it. These were the 2 questions, and this is the graph which is called the heat of hydrogenation graph. We have these graphs for alkanes also, for alkenes also, for almost everything, to determine which is more stable. That is how actually we design the theories which help us to identify which is more stable, alkene or alkane. We just don't know just by seeing the alkane. We measure the heat of hydrogenation, plot it like this, and then we observe the trends, and we actually define the theories. How can we determine the stability and the instability of whatever alkanes, alkenes, alkynes. So this was the end of the lecture. Final question. I hope you have liked the lecture. Please go through all the questions again. If you have not followed me somewhere, start from there again, and so that you don't miss me at any point. Thank you.